We're now going to turn our attention to simple algebraic extensions. And we're going to see that they're much more interesting than the simple transcendental extensions. So let's suppose we have one. So let's suppose k adjoin alpha over k is a simple algebraic extension. This means, just as a reminder of the definition, alpha is a0, I should say, a0 of a non-zero polynomial with coefficients in k. So alpha is a zero of some of them. So for example, we saw earlier that for the polynomial q adjoin I over q, one such polynomial that would work is t squared plus 1, has I as a 0. Of course, there's lots of polynomials that work. I could have taken t squared plus 1 and multiplied it with literally anything. This also has I as a 0 because it will make the left term in the product 0. So there's not a unique polynomial that works. There's an infinite number of them. But there is one. And why? Well, that's the definition of being algebraic. You satisfy a polynomial equation. Now, of all of the ones that satisfy, of all the polynomials that have alpha as a 0, there is one such polynomial of smallest degree. Why does one such polynomial of smallest degree exist? Well, you do a well-ordering principle argument. Let's let S be the set of all degrees of polynomials such that both the polynomial is non-zero and P of alpha is 0. Since alpha is algebraic, there is at least one polynomial that such that non-zero polynomial that alpha satisfies, and its degree is going to be in this set. So this set is non-empty, as alpha is algebraic. It would be empty if alpha was transcendental, but it's non-empty. And so by the well-ordering principle that you learn whenever you take, I don't know, set theory or ring theory, or I think even number theory, this tells us then that S has a least element. And that least element is the one necessarily of smallest degree. Now, in fact, S doesn't have one least element. S has an infinite number of least elements, right? So t squared plus 1 is going to be the least element for if alpha was I, but you could have multiplied that by like 2. So 2t squared plus 2 also has I as a root, and it's also a polynomial of minimal degree. So there's one such polynomial of smallest degree. Let's put this in a thought bubble. With leading coefficient 1. There's one and only one that has that property. Smallest degree is clear from this argument. And once you demand that the leading coefficient is 1, let me show you what happens and how you can deduce uniqueness. So existence is fine. I've shown you how to find it. You look at the guy of smallest degree from the well-ordering principle, and you divide by the leading coefficient to make the leading coefficient 1. For uniqueness, suppose P and Q are two such polynomials. In particular, they're both monic. That is, they have leading coefficient 1. That's what monic means. P minus Q has degree less than, well, the degree of P, which happens to also be the degree of Q, because they're both of smallest degree. So it has degree less than them. But the only way, well, let me say one more thing. And what happens when you plug in alpha into P minus Q? Well, P of alpha minus Q of alpha is 0 minus 0 is 0 because alpha is a solution to both of them. So P minus Q is a polynomial of smaller degree than P and Q. Remember, these were of the smallest degree ones. And it also has alpha as a root. This is a contradiction, as P and Q have the smallest degree among polynomials with alpha as a root. Well, I guess it's not quite a contradiction, but something terrible has gone wrong. What we must conclude from this is P minus Q is 0. So I guess, let me fix this slightly. We conclude P minus Q must be 0. Because that's the only polynomial of a smaller degree that could possibly have alpha as a root, the 0 polynomial, which has everything as a root. So that tells us that P is Q, and this polynomial is unique. All right, so let me just backtrack here. If you have a simple algebraic extension, then alpha, the guy you're adding in, since is an algebraic number over k, so it's a root of a non-zero polynomial over k. Among all of those polynomials, there is one and only one that has the smallest degree and is monic. This is the monic condition. One and only one. That polynomial is therefore special. It's something that is sort of, we say canonically, but it's something that is naturally attached to alpha. So let me give you a definition. Let use my correct highlighting here. Let L over K be a field extension. And let's take some alpha in L, which is algebraic over K. So like the alpha from before. Then the minimal polynomial of alpha over K is the unique monic polynomial over K of smallest degree that alpha satisfies. And in this class, I'll denote it by M sub alpha of T. M for minimal, alpha to remind ourselves what the element this minimal polynomial is a minimal polynomial for, and then of course it's a polynomial, so of T. And this of course is an element of K adjoint T.